Good morning, students. Myself, Vijay Shankar from PC Department, Civil Engineering College. Today, we are going to discuss about the convolution and the correlation, the third one. That is, already we discussed the properties of cross correlation in energy and the power. Now we go for discussion about the autocorrelation, the properties of energy and the power signals. Autocorrelation. So the autocorrelation function gives a measure of match or similarities or relatedness or the coherence between a signal and its a time delayed version. This means that the autocorrelation function is a special form of a cross correlation function. It is defined as a correlation of a signal with itself. Correlation is nothing but a similarity, relatedness, or it's a coherence between the signals and it's a time delayed version. The formula itself, the x of t and x of t minus tau dt, the integral minus infinite to infinite, is autocorrelation function. That's not the different signals here, the same signals. It is defined as a correlation of a signal with itself. The autocorrelation is defined separately for energy and the power signals. Autocorrelation for energy signals R11 of tau is equal to R of tau. So actually, for cross correlation function, we represent R12 of tau. For autocorrelation, R11 of tau, no need of 1, you can write directly, you can write as R of tau. Simply. Autocorrelation function, R of tau is equal to. What is the formula here? One signal is a normal signal, x of t. Another signal is a delayed version with the tau samples, x of t minus tau with respect to the t. You can take any one is a complex x of t with the x star of t minus tau into dt. The same signals. Previously, it is a different signals means x1 and the x2. Now it is autocorrelation function. Where tau is called the delayed parameter and the signal x of t is defined, shifted by the tau samples. If x of t is shifted by the tau in negative direction, if it is a positive direction, we get the minus tau. If it is shifted in the negative direction, x of t plus tau into d. You can keep in for any one of the signal is a complex. So x of t plus tau, x star of t dt. Both are the resultant is the same. Okay, my dear students. And the properties of autocorrelation, the energy signals. So first property saying that the autocorrelation function exhibits conjugate symmetry. That is R of tau is equal to R of minus tau conjugate or conjugate of minus tau, both are the equal. That you can prove the function R of tau is equal to integral minus infinite to infinite. If it is shifted in a positive direction, x of t is equal to x conjugate of t minus tau dt. Got my students. Now take the conjugate on both sides. R of tau, R conjugate of tau is equal to integral minus infinite to infinite. The x of t, now it is a conjugate, x conjugate of t. Conjugate of conjugate is a real function, x of t minus tau dt. Got it, my students? Now change the value, the R conjugate of tau is now the minus tau is equal to integral minus infinite to infinite, x conjugate of t, x of t minus of minus tau becomes a plus tau into dt. Now both are equal here. R of tau is equal to R conjugate of minus tau. Is the first property in the autocorrelation function for energy signals. Okay. Now the second property, the value of autocorrelation function of energy signal at origin, that is tau is equal to 0, is equal to the total energy of that signal. So what they are saying, the R of 0 is equal to energy signal E is equal to integral minus infinite to infinite the squared magnitude of x of t into dt. You know, this is the formula for the energy signal we studied in the orthogonality function. What is autocorrelation function? Formula, the R of tau is equal to integral minus infinite to infinite x of t, x conjugate of t minus tau dt. Tau is equal to 0. R of 0 is equal to integral minus infinite to infinite x of t, x conjugate of t minus 0 into dt. That is equal to integral minus infinite to infinite x of t, x conjugate of t, x of t and x conjugate of t dt. What is x of t and x conjugate? Is nothing but the squared magnitude of x of t on squared magnitude of x of t dt. R of 0 is equal. That is nothing but the energy signal E is equal. Therefore, the R of 0 is equal to energy signal E integral minus infinite to infinite squared magnitude of x of t. Okay, my dear students. And the third example saying that if tau is increased in either direction, the autocorrelation R of tau reduces. As the tau reduces, autocorrelation function R of tau is increases. As the tau is increased in the direction, the autocorrelation function is reduces. Now, tau is reduces, autocorrelation function is increases. Vice versa it is. Increases, and it is a maximum at tau is equal to 0 at the origin. Therefore, R of tau is less than or equal to R of 0. R of tau is less than or equal to R of 0 for all the tau. Okay, for this, to prove this function, consider the function x of t and the x of t plus tau. T plus tau means advanced function is always greater than the equal to the 0 if it is a squared. Like one signal, if I am considering the x of t, another signal x of t plus tau, advanced function, or the shifted in the negative direction. Now combining the two functions, x of t plus r minus x of t plus tau, and it is a square, is always greater than or equal to the 0 since it is squared. Always greater than or equal to the 0 since it is a square. So expand this function, x square of t plus x square of t plus tau, a square plus b square plus 2ab, 2 into x of t plus tau. When we take as a plus value of it is a minus 2ab is greater than or equal to 0. Okay, my dear students. Now the x square of t, the square terms you can keep in the left hand side only. X square of t plus tau is greater than or equal to. You can write it, get it in the right hand side. Plus is becomes a minus, minus becomes a plus. Again, it is a plus or minus only. 2 into x of t, x of t plus tau. Got it, my dear students? Integrate on both sides and take the magnitude here. Integral minus infinite to infinite, the total term. I'll split the two parts. X of t square plus integral minus infinite to infinite, the squared magnitude of x of t plus tau is greater than or equal to 2 into, apply here also the integral value, the minus infinite to infinite is the product it is. You can write only the single integral x of t and x of t plus tau dt. Here also dt, my dear student, with respect to the time we are applying. Got it. Now observe here, in the right hand side is an equation for the 2 into the integral x of t and x of t plus tau. This autocorrelation function only, the r of tau is equal to this r of tau. And in the right hand side, left hand side, the energy signal is energy signal, and its advanced function is also the signal only, the tau is equal to 0, that is energy only, E plus E, both are energy signals. II-E is equal to, II-E is greater than or equal to r of tau, and E is equal to, not the 2 into tau, 2 get cancelled, and E is greater than or equal to r of tau. What is the E? We got a tau is equal to 0. So the tau is equal to 0 means r of 0. When the energy signal at tau is equal to 0 only, r of 0 is greater than or equal to r of tau. Okay, my dear students. Since r of 0 is equal to E, its tau is increases and the tau is reduces, r of tau autocorrelation function is increases. Or otherwise, the tau is increases in either direction, the autocorrelation function r of tau is decreases. Means r of tau is less than or equal to r of 0 when the tau is goes to the 0. You see that as tau reduces, autocorrelation function r of tau is increases, and it is maximum at tau is equal to 0. Maximum at tau is equal to 0. Got it, my dear students? Then the fourth property of autocorrelation in the energy spectral energy signal, that is nothing but here the energy spectral density function psi of omega. Energy spectral density psi of omega. The first property saying that is r of tau is equal to r conjugate of minus tau. And second property saying at tau is equal to 0, the r of 0 is equal to energy signal. And third property saying that as the tau reduces, autocorrelation function is increases, and it is maximum at tau is equal to 0. Nothing but r of 0 is greater than or equal to r of tau. And fourth property, there is a relation between of the energy spectral density and the autocorrelation is Fourier transformation pair. R of tau autocorrelation function considered as a time domain function. Applying the Fourier transformation, you get the psi of omega as a frequency domain function, energy spectral density. The relation between of autocorrelation and energy spectral density is a Fourier transformation pair. The autocorrelation function r of tau, energy spectral density psi of omega, or energy signal form a Fourier transformation pair. Okay. Now you can prove the function. What is a pair here? Saying that this is a x of t signal. You know the Fourier transformation means x of t as the input signal. Applying the Fourier transformation, you get the x of omega. The definition saying the x of omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt. Now x of t is r of tau and x of omega is a psi of omega. So psi of omega energy spectral density is equal to integral minus infinite to infinite r of tau as an x of t signal e power minus j omega let it here the take the t as the tau, here also the tau, and with respect to the tau only can apply. Both all the t variables here with the tau variables. What is R of tau? As per the definition of the autocorrelation function, integral minus infinite to infinite x of t. One signal is a normal signal, another signal is a delayed version. X of t minus tau into dt is R of t signal, R of tau signal, sorry, e power minus j omega tau d tau. Now simplify this integral. Put the one integral as x of t into dt. The remaining is a tau functions. Integral minus infinite to infinite x of t minus tau e power minus j omega tau d tau. In the second integral, by using the time shift property, what is the time shift property saying? X of t minus t naught. Its a Fourier transformation is when the signal is delayed with the t naught samples, the frequency function is multiplied with the negative exponential of the t naught, whatever the samples we shifted, x of omega. Now here the t minus tau, the tau samples are shifted. Integral minus infinite to infinite x of t dt. The tau sample shifted means e power minus j omega tau and the x of omega. X of omega. Got it, my dear students? What is the left hand, the another integral here? Integral minus infinite to infinite, okay, sorry. X of t e power minus j omega t dt. It is also the similar to that of the, not the, here the x of t, not the tau, sorry. Integral minus infinite to infinite. E power x of t e power minus j omega tau dt into x of omega. Okay, my dear students. So in this a small modification you have to do, my dear students, to get the e power x of omega to the x of e power. So the x of t and the x of t minus tau dt e power minus j omega t dt. So one integral we convert as a e power minus integral minus infinite to infinite x of t into e power minus j omega t. You can multiply the dt in this function, and the integral minus infinite to infinite x of t minus tau. Before writing the time domain shifting time shift property, okay, you remove this I multiply the e power minus j omega t here, x of t minus tau e power minus j omega tau. Take the another function here, the e power plus. Okay, you see the r of tau is equal to r of tau into e power minus j omega tau d tau and e power minus j omega t. And here also if take the e power minus j omega t and the e power plus j omega. Plus and minus, there is no any change in the function, whatever here, into d tau. Okay, e power minus j omega t and e power plus j omega. So in the first integral, the x of t e power minus j omega t dt as x of omega. X of omega. In the next one here, the integral minus infinite to infinite x of t minus tau e power, take the common here, the e power j omega t minus tau d. So the signal is the same here. Both the signals are the same. X of omega, and here the x of t minus tau. Here also the x of t minus tau only. Got it? So let the t minus tau is equal to n. Let the t minus tau is equal to n. In the second integral, we have the Fourier transformation of r of tau is equal to x of omega, and the t minus tau is equal to n, x of n e power j omega n into dn. Because the dt is equal to d tau is equal to dn is there. It's a minus value. The conjugate term. So what we get with the finally the x of omega into integral minus infinite to infinite x of t minus tau we have here, x of n e power j omega t minus tau, that is also the one, and the dn is equal to, actually the t minus tau is equal to n. We need the d tau here. The d tau is changes as minus d tau is equal to dn. Means my d tau is equal to minus dn. Minus, you can keep here the minus value as omega, x of omega as x of minus omega, then it is becomes dn only. Dn value, as we can keep is a minus. So x of omega into, actually this term is x of minus omega, the negative values, the conjugate term. Why it is a minus, we can take suppose if it is a take as a conjugate term, x conjugate, x of omega and x conjugate of omega, it becomes of x of omega square, or the squared magnitude of x of omega. Nothing but the psi of omega. R of omega, it's a Fourier transformation. We got as psi of omega. Got it, my students? So the four properties we have. The first property is saying in the energy signal, R of tau is equal to R conjugate of minus tau for autocorrelation function in energy signals. Second property is saying R of 0 is equal to energy signal at tau is equal to 0. And third property is saying that is tau is reduces and the R of tau is increases at the maximum at tau is equal to 0. Is R of 0 is greater than or equal to R of tau at tau is equal to 0. And fourth one, the autocorrelation function and energy spectral density, the Fourier transformation takes psi of omega. Psi of omega. Okay, so four properties for autocorrelation function. Now the properties of autocorrelation function for periodic signals. Periodic signals, energy signal is equal to integral minus infinite to infinite squared magnitude of x of t dt. Okay. What is the power means? The power signal is a limit t tends to infinite 1 by t because it's a periodic signals. Power signals are all the periodic signals only. The energy signal squared magnitude will get x of t x conjugate of t dt. Okay. The conjugate, it is a delayed version. R of tau will have in terms of the limit t tends to infinite. So R of tau is equal to limit t tends to infinite 1 by t the integral t x of t x conjugate of t minus tau dt. The properties of autocorrelation function for power signals. The properties of autocorrelation function for power signals. First property, the same what we have in the for energy signals, R of tau is equal to R conjugate of minus tau only. Okay, let us see that also. R of tau in the power signal, the formula is 1 by t, the integral minus t by to the t by 2 as a limit t tends to also, limit t tends to infinite. X of t, another signal is a delayed and the complex function t minus tau deta, or the deta dt. But take the conjugate on both sides. Conjugate of R of tau, the one limit t tends to infinite, 1 by t, the integral minus t by to the t by 2. X of t, now it becomes a conjugate, and conjugate of conjugate it becomes a real function, x of t minus tau dt. And substitute tau as minus tau, limit t tends to infinite, 1 by t, integral minus t by to the t by 2, x conjugate of tau t, and now it is becomes of shifted in the negative direction, t plus tau dt. Now it is also the R of tau only, the power signal. So R conjugate of minus tau is equal to R of tau. Got it, my students? The second property in the energy signal at tau is equal to 0, R of 0 is equal to energy signal. Now here also the second property is also the same. R of tau is equal to 1 by t, the limit t tends to infinite, integral minus t by to the t by 2, x of t, x conjugate of t minus tau dt. Okay, at tau is equal to 0, at tau is equal to 0, the R of tau, R of 0 is equal to limit t tends to infinite, 1 by t, the integral minus t by the t by 2, x of t, and the tau is 0 means x conjugate of t dt. What is x of t and x conjugate of t? The squared magnitude. Limit t tends to infinite, 1 by t, the integral minus t by to the t by 2 is the squared magnitude of x of t dt. So actually the integral minus infinite squared magnitude of x of t dt is energy signal, and with respect to the t, not with respect to, if the limit t tends to infinite, 1 by t is a power signal p. So R of 0 is equal to p. The second property, R of 0 is equal to p. And third property is also the same, but the autocorrelation function R of tau has maximum value at origin. R of 0 is greater than or equal to R of tau, or R of tau is less than or equal to R of 0. What we are deriving the expression is the same in the energy signal and the power signal, only the change is limit t tends to infinite, 1 by t, the integral minus t by the t by 2. Okay, take the signal x of t, another signal is x of t plus tau, combine the two functions, and it is greater than or equal to 0. Greater than or equal to 0. Okay, so only the limit t tends to infinite, 1 by t, the integral minus t by to the t by 2 can write. Then the third property is also it get the same. Got it, my students? And fourth property, autocorrelation function R of tau is a Fourier transformation pair of, there it is energy spectral density, now here it is a power spectral density S of omega. Power spectral density x of S of omega. Psi of omega is energy spectral density, and S of omega is power spectral density. So here also the autocorrelation function is a Fourier transformation pair of x of omega. Okay, Now we have the fifth property. The autocorrelation function is periodic with the same period of periodic signal itself. R of tau is equal to R of tau plus or minus n into t. We know the x of t is equal to periodic signal x of t plus capital T. With the time period t, it is repeated, the periodic signal. For the discrete time signals, x of n is equal to x of n plus capital N, where n is a fundamental period, where t is the fundamental period. Now it is R of tau is plus or minus n into t. R of tau is a time domain function that is equal to R of tau is plus or minus n into the t. The n is a number of multiples when n is equal to 1, 2, 3, and so on. And the t is a fundamental. Okay. Now, what is the energy spectrum? Density spectrum. What is the energy density spectrum? We are already saying that it is energy density spectrum. You can represent it as psi of omega. Okay, psi of omega. We know the energy signal that mathematically E is equal to integral minus infinity squared magnitude of x of t dt. Okay. The spectral density, it is a distribution of energy or power of a signal per unit bandwidth as a function of frequency. Either it is a energy or power of a signal per unit bandwidth as a function of frequency. Energy signals with finite energy and zero average power. Zero is less than energy signal less than the infinite, and P is equal to 0 are called energy signals. Means energy is varies in between of 0 to infinite. At that time, the power is equal to 0. You can call it as energy signals. Okay. And the power signals means 0 is less than the P less than the infinite, and the energy is infinite. Then we can get this you can say it is a power signals. Normalized energy. The normalized energy or the single energy of a signal x of t is defined as the energy is dissipated by a voltage signal applied across 1 ohms resistor or by a current signal flowing through the 1 ohms resistor. Mathematically, E is equal to integral minus infinite squared magnitude of x of t dt. The energy of a signal exists only if E is finite. That is, only if 0 less than the E less than the infinite. Got it, participants? The energy density spectrum, in that the energy signal is equal. Okay. And you have to go for the proof of the Percival's theorem. Already we did in the Fourier transformation. E is equal to integral minus infinite x of t square dt 1 by 2 pi into the squared magnitude of x of omega, the angular frequency, or without 1 by 2 pi, the x of omega d omega df. The squared magnitude of x of omega is nothing but there is a psi of f only, not the psi of f or the psi of omega in terms of the normal frequency or in terms of the angular frequencies. Got it, my students? And here you can take the proof of this Percival's theorem. Consider the function x of t with apply the Fourier transformation x of omega. X conjugate of t is x conjugate of minus omega. For the negative values of omega, it's a conjugate term. So we know the energy signal x squared magnitude of x of t, we can write as x of t x star of t dt. Take the x of t as an inverse Fourier transformation x of t 1 by 2 pi integral minus infinite the x of omega into e power plus j omega t d omega. As we can take as a conjugate function, it becomes of x conjugate of omega, and the positive values becomes negative value. Substitute in that one, the energy is equal to integral minus infinite x conjugate as 1 by 2 pi integral minus infinite to infinite x conjugate of omega e power minus j omega t d omega as of x conjugate of t. Another x of t is there. X of t. Got it, my students? X of t into dt is equal to. You can simplify that's 1 by 2 pi integral minus infinite to infinite x of omega, it is integral minus another integral minus infinite to infinite x of t e power minus j omega t dt is again you'll get the x of omega only, and the integral minus infinite to infinite x conjugate of omega d omega. This is also one of the definition of the Fourier transformation, not the one of the definition only. 1 by 2 pi into x of omega and integral minus infinite to infinite x conjugate of omega d omega. That is equal to 1 by the 2 pi. You write this in the integral minus infinite to infinite x of omega and x star of is x squared magnitude of x of omega. This is the first term. Now omega is equal to 2 pi f. D omega is equal to 2 pi into df. Okay. Now substitute here. The energy E is equal to 1 by 2 pi integral minus infinite to infinite squared magnitude of x of 2 pi f into d omega is a 2 pi into df. The 2 pi get cancelled, and energy is equal to, in terms of the normal frequency, integral minus infinite to infinite. Here write the shortcut notation x of f into df. The third one. Percival's theorem of the energy signals, or it is also called as a Rayleigh's energy theorem. Got it, my students? This is called the Percival's theorem for energy signals, also called as Rayleigh's energy theorem.